In this video we are going to look at the work for Unit 3 on strings and springs. So the specification says that we need to be able to solve problems involving light strings and springs which obey Hooke's law, and that we need to be able to understand and use elastic potential energy. It's important to remember that an elastic string can be stretched, but it can't be compressed. If you've got an elastic string whose natural length, that's its length when it's just hanging freely, is of length A, and then we stretch it, give it an extension of x, then Hooke's law says there'll be a tension in the string of size lambda x over A, where lambda is the modulus of the string and A is the natural length of the string. And once stretched, the string is going to be storing some elastic potential energy given by lambda x squared divided by 2A. On the other hand, elastic springs can be stretched or compressed. The results for the extension of an elastic spring are exactly the same as the results for the extension of an elastic string. If we compress the spring from its natural length, then there will be a thrust in the spring, trying to get the spring back to its natural length, which also obeys Hooke's law. So thrust is equal to lambda x over A, and also the elastic energy stored in a compressed spring is also given by lambda x squared over 2A, where the compression is x. So let's now have a look at a few examples on strings and springs. So in the first example, we have a particle is attached to one end of a light elastic string of natural length L meters and modulus of elasticity lambda newtons. The other end of the string is attached to the ceiling. The particle hangs in equilibrium. The length of the string is 0.95 meters when the weight of the particle is 30 newtons, and is 1.15 meters when the weight of the particle is 70 newtons. We have to find the value of L and lambda. So we'll start by drawing a diagram. So we start with the string just hanging freely, and then we'll attach the particle of weight 30 newtons to the string, and we then know that the total length of the string is 0.95 meters, so the extension of the string in this position is 0.95 minus L. If we put the forces acting on the particle onto the diagram, we have the weight of 30 newtons and we have the tension. Because it's hanging freely in equilibrium, we have T1 must equal 30 newtons. And applying Hooke's law, we've got lambda times by the extension 0.95 minus L, all divided by L, must equal 30. In other words, we have the equation lambda times 0.95 minus L must equal 30L. And we now carry out a similar analysis on the situation when we have the 70 Newton particle hanging from the string. In this case, the total length of the string is 1.15 meters, so the extension in this case is 1.15 minus L. Again, we have a weight of 70 newtons and a tension. We know that the tension must now equal 70 newtons, and Hooke's law tells us that the tension must be lambda times by 1.15 minus L divided by L. So we've got lambda times 1.15 minus L divided by L must equal 70. So we have our second equation, lambda times 1.15 minus L must equal 70L. So looking at our two equations that we've got there, we've got lambda times 0.95 minus L equals 30L, lambda times 1.15 minus L equals 70L. The easiest way of solving these two equations is to divide one equation by the other equation. So if we take equation 2 and divide it by equation 1, we obtain lambda times 1.15 minus L divided by lambda times 0.95 minus L equals 70L over 30L. But on the left hand side the lambdas cancel out, on the right hand side the L's cancel out, so we're left with 1.15 minus L divided by 0.95 minus L equals 7 divided by 3. If we multiply up to clear the by 0.95 minus L and by 3 to clear the fractions, we obtain 3.45 minus 3L equals 6.65 minus 7L, which simplifies down to 4L equals 3.2, so L must be equal to 0.8 meters. Substituting this into equation 1, the left-hand side is 0.15 lambda equals 30 times 0.8, which is 24. So we've got lambda is 24 divided by 0.15, which is 160 newtons. Let's move on to a second example now. In this case, we've got a piston of mass 0.8 kilograms. It's enclosed in a horizontal tube and attached to a light spring of natural length 0.2 meters and modulus of elasticity 625 newtons. The other end of the spring is attached to the end of the tube. Initially, the piston is held at rest at a point A with the spring compressed a distance of 0.1 meters. So that AB is the compressed length of the spring. First, so we have to calculate the elastic energy stored in the spring. So we know that elastic energy is given by lambda x squared over 2a, and we know that the compression of the spring in its initial position is 0.1 meters. So the energy stored is going to be 625 times by 0.1 squared divided by 2 times the natural length, which is 2 times 0.2, which gives us a energy of 15.625 joules. We then release the piston, and during the subsequent motion it's subjected to a resistance to the motion of constant magnitude 46 newtons. Now at the moment, at the start position, we've got some elastic energy. This elastic energy is being converted into kinetic energy when the spring reaches its natural length. But we've also got to do some work against the resistance. So we've got a work energy balance, which is telling us that the elastic energy that we lose is going to equal the kinetic energy gained by the piston together with the work done against the resistance. When the spring reaches its natural length, there is no compression, there is no extension, so there is no elastic energy in the spring when it's reached its natural length. So the elastic energy lost is the 15.625 joules that we've just calculated. The kinetic energy gained by the piston is a half of the mass of the piston times by v squared. The mass of the piston is 0.8, so we've got a half times 0.8 times v squared. The work done against the resistance, well, the resistance is 46 newtons, and we've been moving 0.1 meters against that resistance. So the work done against the resistance is going to be 46 times by 0.1. Rearranging this equation, we get 11.025 is equal to 0.4 times v squared, and dividing by 0.4 will give me v squared is 27.5625, and then square rooting we obtain the speed of the piston as 5.25 meters per second. And we'll now move on to our final example. We have an object P of mass 3 kilograms is attached to one end A of a light elastic string of natural length 2 meters. The other end B of the string is attached to a point on the ceiling. The modulus of elasticity of the string is 294 newtons. So to begin with, we're told the particle is suspended in equilibrium with A vertically below B, and we have to calculate the extension of the string AB. So we need to start by drawing a diagram. Initially just have the natural length clearly marked on the diagram, then put the mass in its equilibrium position and show the extension that we've got. The forces need to be put onto that diagram. So we've got the weight, which is 3g, and we've got the tension, T. For the equilibrium position, we must have T equals 3g, but Hooke's law tells me that T is lambda times the extension divided by A. So in this case, that is 294 times by x naught divided by the natural length of 2. And that's got to equal 3g, which is 29.4. So if we rearrange that, we end up with x naught equals 0.2. The extension of the string when P is in equilibrium is therefore 0.2 meters. Now for the next part of the question, we're going to raise the particle P so that it's only 1.2 meters below the ceiling. We're going to release it from rest, and we wish to calculate two things. First of all, its maximum speed in the subsequent motion, and secondly, the lowest point below the ceiling that it reaches. So there's the starting position shown in the diagram. In subsequent motion, when it reaches its maximum speed, there's going to be no acceleration, because dv by dt, rate of change of the speed or rate of change of the velocity, gives us acceleration, but if we're going to have a maximum speed, there can't be any acceleration. The point where there's no acceleration is the point where there is no resultant force, which is of course the equilibrium position. So the maximum speed will occur as the particle passes through its equilibrium position. To find this maximum speed, we can use an energy balance. So, in the initial position, the particle is 1 meter above its equilibrium position, and it's going to be losing some potential energy as it falls from the starting position through to the equilibrium position. That potential energy that we've lost is going to be converted into kinetic energy of the particle together with some elastic potential energy stored in the spring. So we've got the Ke gained together with the elastic energy gained. The potential energy that we've lost is mgh, so that is 3, the mass of the particle, times g, times by the 1 meter that the particle has fallen through. The kinetic energy gained is a half mv squared, so that's a half times 3 times v squared. And the elastic energy that's been gained, well, the extension of the spring in its equilibrium position is 0.2 meters. So we've got lambda times by x squared divided by 2a, so that's 294 times 0.2 squared divided by 4. If we work out each of the terms separately, we have 29.4 equals 1.5 v squared plus 2.94. So that ends up giving me v equals 4.2 meters per second. We now want to find out how far the particle drops below the ceiling. So if we let h equal the depth that the particle falls beneath the ceiling, then in that position there, the distance that we will have dropped from the start position will be h minus 1.2. And at the bottom, the extension of the spring will be h minus the natural length, h minus 2 meters. Now again, we're going to use an energy balance. So we've lost some potential energy in the drop, and we have gained elastic potential energy. There won't be any kinetic energy at the bottom because the speed will be 0 at the bottom. So the potential energy lost is going to be mgh, so that's going to be 3 times g times the distance that we've dropped, which is h minus 1.2. The elastic energy gained is going to be lambda x squared over 2a, where x is h minus 2. So the elastic energy gained is going to be 294 times by h minus 2 squared over 2 times the natural length, which is 2 times 2. So looking at that equation, we can certainly tidy it up by saying that 3g is 29.4. If we divide each side by 29.4, we're going to end up with h minus 1.2 is 2.5. That comes from the 10 divided by 4. Lots of h minus 2 squared. Multiply the brackets out and tidy the quadratic equation up. We've got 2.5h squared minus 11h plus 11.2 must equal 0. And using our calculator to solve the quadratic equation, we end up with h is either 3.057 or 1.527. Now when h is 1.527, the string is still slack, so the particle is falling with acceleration 9.8 meters per second squared. So at that point it can't possibly be at stationary and at its lowest point. So we must have a solution which is more than 2 meters. So the solution we're going to take is that the lowest point is 3.057 meters below the ceiling. Finally, we need to consider some of the modelling assumptions made in the course of answering this question. First of all, if the string wasn't light, then the answer to B1 would certainly be different, or is very likely to be different at any rate, because we would have to start taking into account the fact that there is some kinetic energy in the string itself, and also there will be changes in the potential energy of the string. There are lots of other assumptions that have been made in the course of answering this question. We've been treating the object as if it's a particle. We're certainly assuming that the elastic limit of the string has not been exceeded. And we're certainly ignoring any air resistance.